Okay, I think probably this slide gonna be better answer to you, Ronan, about the MIC is the target. Okay, right now we know the target. We have to have like the plasma drug concentration more than the MIC. But do you think it's always true? No, because sometimes we have the bacterial infection in the sensory organ, like a prostate gland, eyes, or the CNS, those kind of things. Blood plasma drug concentration probably not a good idea. And what we can do about that? So you have to know the drug other pharmacokinetic parameter, which is a volume distribution, because a volume distribution can refer and make you think about that the drug can distribute to the deep tissue or not. Okay. Just to remind you again, MIC data, just the data of concentration to tell you inhibit the growth of the bacteria. Susceptible result, it doesn't refer to you, no resistant. The MIC of isolate right here, so we can use the MIC 50 or we can use the MIC 90, but the MIC 90 is going to tell you 90% of the population that show up this MIC. Okay, plasma drug concentration and the tissue concentration, we all know is not the same. But keep remind that even though MIC data is the best we can do, but you have to know where is the location of infection. Okay, now we're going to moving on to design dosing regimen. I'm sure everyone familiar with this picture that is a concentration and versus time. And show you right here is a non-IV route of administration. We agree for that. That's plasma drug concentration need to stay above the MIC. And we're going to draw the data from the MIC to predict plasma drug concentration. And we're going to take other pharmacokinetic parameter to take account to design dosing regimen. That is a Cmax, half-life, and the AUC. AUC right here, I try to find the data, but the paper, some paper, they have a different, the AUC data here. So I'm not going to talk the AUC much, but I'm going to show you how I calculate the dosing regimen based on the Cmax and a half-life. And plasma drug constant, And we're going to incorporate the pharmacokinetic data and pharmacodynamic data. We all know that for this curve. And pharmacodynamic data, we're going to draw for this picture that we call this concentration as a minimum effective concentration. But for antimicrobial drugs, it's going to be MIC, right? Because we need to have plasma drug concentration stay above MIC. That's going to be the minimum effective concentration, or the MIC is the same thing in this case. Okay. Let's say we agree that plasma drug concentration need to stay above the MIC. And how high? Okay, let me show you one principle here. This is a bacterial inoculum that causes infection here. The purple dot represents to the susceptible isolate, and the red dot it represents to the resistant isolate here. It is a normal in nature. Every inoculum, you have to gonna see like the mix of the resistant and the and susceptible is normal here. Okay, we prescribe the dose, and that dose it turned out is a subtherapeutic. What happened here? The dose or the Cmax is not stay above the MIC. What happened to the? Let me read the chat first. Not yet. I will answer you your question, Ronan, but not yet. Yeah. So this is go only the time dependent. I'm gonna show you the concentration dependent and time dependent how to decide dosing regimen. I will show you right after. Just be patient. Hang on with me. Okay. All right. I want to show you a couple things here. Okay. You show right here, not even beyond the MIC. What happened? We just killed some of the susceptible isolate, right? And probably reinforce or develop have the resistant bacteria. Okay, that's what happened here. Okay, we increase the dose or we do the better job about the design dosing regimen, but it turned out we don't do well enough. We just kill the susceptible bacteria, but we don't kill the resistant bacteria. Okay, so we do better by increase the dose, or maybe the shorten the dosing interval. That is the target for us. That is, we kill them all, whip them out, eradicate all the population, both susceptible and the resistant bacteria. And that is the goal for us. How do we design dosing regimen? Because we need that. Why? Because you know what? The minimum concentration that causes the kill or the eradicate all the population is called mutant prevention concentration. But if we design the dose following to the mutant selective window in this one, it's not good because we push to have susceptible die, but the resistant bacteria still survive. That's what happened to Gala. 3 weeks later, she has a recurrent UTI with the multi-drug resistant because we put this pressure on her inoculum and have the resistant bacteria survive and stay and populate and cause UTI symptom that we see here. So that is our goal for us. And the way they design or the way to calculate the mutant prevention concentration based on the in vitro, we don't know for sure which way gonna do the best in the clinic, but what we know, we use a pharmacokinetic and pharmacodynamic integration. That's gonna be the best way for us right now to try to avoid the mutant selective window. Okay, and that is the principle of the dead bugs don't mutate. I have a question. Do we really want a complete eradication or rather target a significant reduction of initial inoculum? That's a great question. We want to eradicate all the population. And how do we do it? By using PK and PD integration and based on the different type of design dosing regimen. And the concentration dependent, we're going to use that. I'm going to tell you about that later, okay? Thank you for the question.